mc². It's probably the most famous formula in science, really, etched into popular culture.
Absolutely. Everyone knows it.
But what if we told you that a seemingly simple thought experiment involving this very equation can unlock some of the deepest secrets of the universe?
It really can. Our deep dive today focuses on a question that, well, at first glance might just sound like an algebra problem,
Right.
What does the m, the mass, in mc² actually signify when the E, the energy, is set to 1?
And this isn't just about the numbers, is it? It's more like a profound lens to view reality itself.
Precisely. We're going to unpack this query layer by fascinating layer. We want to go far beyond any standard textbook definition you might have encountered.
Okay, so we'll be drawing from a pretty detailed analysis of this specific problem. We'll look at the equations components, the impact of measurement systems, which is often overlooked, I think.
Definitely. And its incredible real-world manifestations, too. Think of us as your guides, really, trying to cut through the complexity.
We're here to give you the clearest, most engaging understanding possible of maybe the most important equation in physics, tailored just for you.
Okay, so where do we start? The equation itself.
Yeah, let's start by dissecting EMA itself.
Yeah.
Because before Einstein, mass and energy were, well, they were like two entirely separate categories in physics, weren't they?
Completely separate. Mass was, stuff, tangible, takes up space, has inertia.
Right, like a rock.
Exactly. And energy, on the other hand, was the capacity to do work. They were conserved, sure, but independently. No connection imagined.
Until Einstein, that distinction was completely shattered by his revolution.
He showed that mass and energy aren't separate at all. They're two sides of the very same coin, interconvertible. Manifestations of a single underlying physical entity.
It's that famous quote, isn't it? The mass of an object is a measure of its energy content.
That's the one. It's a powerful idea.
It really is, because even now they feel so different to us. How did he even start connecting something so tangible, like you said, a rock, with something as abstract as, I don't know, a beam of light?
Well, it started conceptually with the idea of rest energy.
Rest energy. Okay.
This is the concept that an object inherently possesses just a vast amount of energy simply by having mass, even if it's perfectly still.
So when you see mc², the E is really this inherent enormous rest energy.
Primarily, yes, in that specific formulation. And it's crucial to note how our understanding of m itself evolves over time.
Right, because you sometimes hear that old idea that mass increases with velocity.
Exactly. But modern physics has clarified that. We now prefer the term invariant mass, or sometimes just rest mass.
And that's an intrinsic property, something fundamental to the object.
Yes, it's constant for all observers, regardless of how they're moving. What does increase with velocity is the total energy of the object, not its fundamental mass itself.
Okay, that makes sense. So the M in mc² is this intrinsic rest mass.
That's right. So while mc² beautifully captures the energy an object has at rest, it's actually a special case.
A special case of something bigger?
Yeah, of a more comprehensive picture. The full energy momentum relation is EM equals mmc plus PC.
Oh, okay. So M there is the rest mass we were talking about.
Exactly. And P is momentum. So an object's total energy actually comes from two places. Its inherent rest mass energy, and the energy it has due to its motion, its momentum, PC.
Got it. That gives a much more complete way to understand how energy and mass are intertwined, especially when things start moving really fast, near light speed.
Precisely.
So if M refers to this intrinsic rest mass, let's turn our attention to c, the speed of light. It's clearly more than just the speed.
Oh, far more. C isn't merely the speed limit of light in a vacuum. It's a fundamental constant of nature.
The absolute maximum velocity for everything, right? Energy, information, cause and effect.
That's right. Nothing with mass can ever reach it. You can't send a message faster than c. It literally defines the causal structure, the very fabric of space-time.
And the history of measuring it is fascinating in itself. It took centuries.
It really did. From early estimates, like old Romer looking at Jupiter's moons back in 1676.
Right. He got surprisingly close just by observation.
He did, considering the time. Then James Bradley with stellar aberration, and then increasingly precise terrestrial experiments. Fizeau, Foucault, Michelson.
Yeah.
Using ingenious devices like spinning mirrors and rotating gears. They just kept refining the measurement.
Until 1983. That was the big shift, wasn't it?
It was a defining moment, because instead of just measuring C more precisely, the international scientific community actually defined it.
They fixed its value.
Exactly. It's now defined as exactly 299,792,458 meters per second, period.
Which means the meter itself is now based on the speed of light.
Precisely. Our basic unit of length, the meter, is now derived from c and the second. It tells you how truly fundamental c is. Arguably more fundamental than our human concepts of distance or time.
Okay, so we have m as rest mass, c as this fundamental constant, and then there's the c term. That's where the real impact comes from, isn't it?
Absolutely. Squaring c creates a truly colossal number.
We're talking, what is it, roughly 9 times 10 to the 16th?
Yeah, approximately 9 times 10 arnimeters squared per second squared, or, roughly 90 quadrillion. It's this immense number that makes the conversion factor between mass and energy so utterly staggering.
Why squared, though? Is there an intuitive reason?
Well, you can think of an analogy with classical kinetic energy, maybe. Ke equals 1/2 mv squared. Velocity is squared there, too.
Right.
In relativity, c is sort of the universe's characteristic velocity, its ultimate speed limit. So it kind of naturally appears squared in this energy relationship.
And the scale is just hard to grasp. You use the paperclip example.
Right. Imagine if you could convert just 1 gram of mass, about the weight of a regular paperclip, entirely into energy.
Which you can't really do easily, but hypothetically.
Hypothetically, yes. The energy yield would be the explosive force of roughly 18 kilotons of TNT.
18 kilotons. That's equivalent to the atomic bomb dropped on Hiroshima from 1 gram of matter.
Exactly. It's a stark reminder. Ordinary matter isn't just stuff. It's an incredibly dense reservoir of, well, some physicists call it congealed energy.
Congealed energy. I like that.
And that colossal steer term explains why everyday energy changes, like burning wood or chemical reactions, involve mass changes that are just far too tiny to detect.
Imperceptible.
Right. But it's only in extreme events like nuclear reactions that the equation's full power becomes, well, terrifyingly obvious.
Okay. Which brings us perfectly to the central analysis of our deep dive. What happens when we set E1? What does the mass become then?
Ah, yes. This is where it gets really interesting, because the actual value you get for m when E1 depends entirely on the system of units you choose to use.
It's not one single number.
Nope. And this isn't a flaw in the equation, not at all. It actually reveals something powerful about our perception of reality versus fundamental reality itself.
Okay, so let's break that down. Let's start with the system we use every day, the SI system, International System of Units. Energy is measured in joules.
Right. And a joule is a very human-scaled unit. It's roughly the energy you'd need to lift a small apple, maybe 100 grams or so, about 1 meter off the ground. Pretty tangible.
Okay, so if E is 1 joule, what's M?
If we set E 1 joule and EMC, and we use the defined value for C, then we solve for M. You get M equals ECO. So 1 joule divided by that massive C number.
Give you something tiny.
Extremely tiny. It's approximately 1.11265 times 10 to the minus 17 kilograms.
10 to the minus 17. What is that? Femtograms?
Yeah, about 11.1 femtograms. For perspective, that's vastly less than the mass of a single human cell, maybe closer to the mass of a large virus particle.
Wow. Okay, think about that. To get just 1 joule of energy, enough to lift that apple, you only need to convert an absolutely minuscule, almost incomprehensible amount of mass.
It really underscores the point. Matter is just unbelievably concentrated energy viewed through our everyday units.
But then there's another way to look at it, right? The way theoretical physicists often do.
Yes. Using what are often called natural units or sometimes geometrized units.
And the idea there is to simplify things.
Exactly. Theoretical physicists often find it convenient to set fundamental constants like c, the speed of light, and sometimes others like Planck's constant or Newton's g equal to 1.
Just define them as 1.
Yeah. They're essentially stripping away our arbitrary human-scaled concepts like meters and seconds, trying to get closer to the underlying physics where these constants just define the relationships.
So if c equals 1, what happens to E, Sam, behave?
It becomes incredibly simple. E, m times 1 squared, which is just
EM.
EM. So in this framework, if you set the energy E to 1...
And the mass m is also 1.
Exactly. E1 implies N1.
That feels profound. In a system of units, free from our human conventions, a unit of energy is literally identical to a unit of mass. The distinction just dissolves.
It dissolves. It reveals this one-to-one correspondence right at the heart of nature. It suggests that our everyday distinction between, say, a beam of light and a walnut is, in a way, an artifact of our perception and our chosen units. Fundamentally, they're manifestations of the same underlying stuff, for lack of a better word, mass energy.
So this isn't a contradiction, then? Getting 2 different answers for M1 ED1?
Not a contradiction at all. It highlights the difference between perspectives. One is the practical engineering perspective using SI units, which shows the immense energy density of matter in terms we can measure and use.
Like calculating reactor yields.
Right. The other is the fundamental physics perspective using natural units, revealing the inherent identity of mass and energy. Both are valid ways of looking at the equation's meaning.
And regardless of the units you choose, the exchange rate is fixed, isn't it?
Absolutely. That's the core point. mc² defines a universal fixed exchange rate. For every, say, joule of energy that appears or disappears, a specific amount of mass, that tiny 1.1.10 Erie kilograms, must disappear or appear.
And this fixed rate is really the key to understanding the huge difference in scale between, say, chemical reactions and nuclear reactions.
Precisely. Think about chemical reactions, burning wood, digesting food, batteries. These involve rearranging the electron clouds around atoms.
Relatively low energy changes, comparatively speaking.
Right, so the mass changes involved, according to mc², are absolutely minuscule, far, far too tiny to measure with any current technology. Your hot cup of coffee theoretically has infinitesimally more mass than when it's cold because of the heat energy, but it's utterly undetectable.
But then you get to nuclear reactions. Fission, fusion, these involve the nucleus itself.
And the forces holding the nucleus together, the strong nuclear force, are millions of times stronger than the electromagnetic forces governing electrons.
So when you rearrange the nucleus,
the energy changes are enormous, millions of times larger than in chemical reactions. And therefore, the corresponding mass change, what we call the mass defect, is also millions of times larger.
And that mass change is measurable.
Oh, yes. Readily measurable. This mass defect, the delta m, is the m in the practical application of the equation E. That measurable loss of mass is exactly what's converted into the huge energy release.
It really puts things in perspective. The same equation governs both, but the scale factor, C, makes the nuclear changes visible in terms of mass.
Exactly. And we see these principles playing out on the grandest scales and down here on Earth.
Like in stars. Stellar fusion. The cosmic engine, basically.
Indeed. Our sun, all stars, are just magnificent, long-lived demonstrations of mass-energy equivalence in action.
What's happening inside? Hydrogen fusing into helium, right?
Primarily, yes. In the sun's core, under immense pressure and temperature, hydrogen nuclei protons are fused together through a series of steps to form helium nuclei.
But here's the kicker, as they say. The mass of the final helium-4 nucleus is slightly less than the total mass of the 4 initial protons that went into making it.
About 0.7% less, actually.
And that missing mass, that tiny percentage, that's
precisely what gets converted into a tremendous amount of energy photons, light and heat, and neutrinos, according to E4.
And it's this energy pushing outwards that keeps the star from collapsing under its own gravity.
Exactly. It provides the radiation pressure that balances gravity's inward pull. It's a continuous process. Every second, the sun fuses something like 600 million metric tons of hydrogen into helium.
Wow. And in doing so,
it converts about 4.26 million metric tons of its own mass into pure energy. Every single second.
4 million tons per second. That energy output is staggering. Something like 384 yottawatts.
That's the number. It's almost incomprehensible power. And of course, our very existence here on Earth, all life, is a direct consequence of that sunlight, that energy released from mass conversion billions of miles away.
Amazing. And then down here, humanity learned to tap into this principle too. The atomic engine, nuclear fission.
Yes, we figured out how to release energy from mass defect by splitting heavy atomic nuclei like uranium-235 or plutonium-239.
So instead of fusing light nuclei, we're breaking heavy ones.
Right. And again, it turns out that the total mass of the fission products, the smaller nuclei, and neutrons that result from the split is slightly less than the mass of the original heavy nucleus plus the neutron that triggered the fission.
Another mass defect.
Another mass defect. And again, EBC tells you how much energy is released.
And if this process also releases more neutrons,
which it does,
yeah,
then those neutrons can go on to split other heavy nuclei, potentially leading to a self-sustaining chain reaction.
Which can be controlled, carefully managed in a nuclear reactor to generate electricity.
Or allowed to run away, uncontrolled, in an atomic bomb.
And what's truly astonishing, maybe chilling, is that Einstein's equation was used to calculate the immense potential energy yield of fission before the first atomic device was ever built or tested.
Yes, the theory predicted the power. It guided the Manhattan Project. They knew, based on measuring the mass defect, roughly how much energy they could expect to release. It allowed them to anticipate its devastating potential.
It really shows the predictive power of the
And it
physicist.
highlights this efficiency hierarchy, too. If you look at the percentage of mass converted to energy.
Chemical reactions are minuscule, less than 0.0000001%.
Right. Nuclear fission is much better, around 0.1% mass conversion.
Fusion, like in the sun, is even better, around 0.7%.
And then the ultimate theoretical limit is matter-antimatter annihilation, where you get the 100% conversion of the annihilated mass into energy.
That millionfold leap from chemical energy to nuclear energy, it's all down to accessing the much larger binding energies within the nucleus, and therefore seeing a much larger marrow.
Precisely.
But it's not just mass turning into energy, is it? You mentioned earlier, it's a two-way street. Energy can create mass.
Absolutely. The equation works both ways. Amyl ETC, energy can be converted into mass.
And we actually do this.
We do. This is basically the day job of particle accelerators, like the Large Hadron Collider, the LHC, at CERN.
How does that work? They smash particles together at incredible speeds.
Right. They accelerate particles like protons to enormous kinetic energies very close to the speed of light, and then collide them head-on. In those collisions, that immense kinetic energy can be transformed into new particles that weren't there before.
Creating mass from energy.
Exactly. The creation of heavy particles like the top quark or the famous Higgs boson. These particles have significant rest mass. That mass is literally forged from the concentrated energy of the collision, according to mec².
So these accelerators are essentially mc² machines running in reverse.
That's a great way to put it. They are vital working tools that demonstrate this fundamental principle every day. They're at the forefront of discovering the fundamental constituents of matter, using energy to create mass.
Which connects nicely to the deeper theoretical implications, right? Like the unification of conservation laws.
Yes, that's one of the most profound consequences. Before Einstein, back in 19th century physics, you had two separate pillars: the law of conservation of mass and the law of conservation of energy.
You couldn't create or destroy mass, and you couldn't create or destroy energy. They were independent laws.
But Einstein's work showed that neither law is strictly true on its own. Mass can be converted into energy, as we see in stars and reactors. And energy can be converted into mass, as we see in particle accelerators.
So what is conserved?
What's truly conserved is a combined quantity, mass energy. The total amount of mass energy in an isolated system remains constant. Mass can transform into energy, and vice versa. But their sum, using C as the conversion factor, always stays the same.
So it wasn't that the old laws were wrong, just incomplete.
Exactly. They were excellent approximations for everyday phenomena where mass changes are negligible. But relativity revealed the deeper unified picture. It was a monumental step, showing two concepts previously thought distinct were actually just facets of a single underlying conserved quantity.
And we also touched on the full energy momentum relation earlier. mc² plus pc². That's important too.
Very important. It reminds us that mc² is specifically the energy an object has when it's at rest, PO0. The full equation shows that total energy comes from both rest mass energy and energy due to momentum.
And this also explains how massless particles, like photons, the particles of light, can carry energy, right?
Precisely. For a photon, the rest mass error is 0, so the equation simplifies. E equals 0 plus PCR, or simply EPC.
Their energy comes purely from their momentum.
Exactly. It clarifies that energy isn't just tied to mass. It's fundamentally linked to both mass and motion, momentum.
Which brings us maybe to the most modern perspective. mc² tells us how much energy a given amount of mass is equivalent to, but it doesn't tell us why particles have mass in the first place.
That's a crucial distinction. mc² describes the energetic consequence of having mass. The question of the origin of mass itself is answered within our current best theory, the standard model of particle physics, by the Higgs mechanism.
Ah, the Higgs field. The God particle stuff people heard about.
Well, the Higgs boson is the particle associated with the field, yes.
Yeah.
The theory posits that the entire universe is permeated by an invisible energy field, the Higgs field.
Okay.
And fundamental particles, like electrons, quarks, acquire their intrinsic invariant mass by interacting with this field.
So more interaction means more mass.
Essentially, yes. Particles that interact strongly with the Higgs field have a large mass. Particles that interact weakly have a small mass. And particles that don't interact with it at all, like photons,
Remain massless.
remain massless.
And the discovery of the Higgs boson at the LHC back in 2012 was the confirmation of this theory.
It was the crucial confirmation, yes. Finding the Higgs boson provided strong evidence that the Higgs field and this mechanism for giving particles mass is indeed how nature works.
So it's like a two-part story then. The Higgs field is responsible for giving fundamental particles their mass.
And Einstein's relativity, specifically mc², then tells us the staggering energetic worth of that mass.
That's a fantastic summary. Higgs gives the mass, Einstein defines its energy value.
You can put it that way.
So as we kind of wrap up this deep dive, we've journeyed quite a bit. We saw how setting E1 in familiar units reveals mass as this almost infinitesimally small number, really hammering home the incredible energy density locked up in ordinary matter.
But we also saw that in fundamental units, natural units, setting E1 simply leads to M1. It reveals mass and energy as fundamentally the same thing, just viewed differently depending on our measurement conventions.
And ESI itself isn't just abstract theory, it's the master key, isn't it? Dictating the processes that make stars shine, that power our nuclear reactors, that even allow us to create new forms of matter in particle accelerators.
It's absolutely central. It's far more than just a formula. It's a profound statement of unification. It unified mass and energy. It unified the classical conservation laws into a single, deeper law. It's like part of the fundamental grammar of the cosmos.
So here's a final thought for you, our listener. When you look at something completely ordinary, maybe something as simple as a grain of sand on a beach, knowing now that its seemingly tiny, insignificant mass holds enough congealed energy that, if released, could potentially power a small city for days, how does that change your perception of the physical world around you?
How does it change how you think about the very stuff that you yourself are made of? It's quite something to contemplate.
What will you choose to explore next, armed with this deeper understanding of perhaps the most famous and most profound equation in science?